This is Project 1 Aircraft Carrier Arrestor Gear. Now, the assignment for this project is to design a damping system that helps land a plane in an aircraft carrier. As we know, the aircraft carriers have a very short runway. This means that the plane has to land in a very short amount of time in a short amount of distance. Now, here's a system that describes how a plane usually lands onto an aircraft carrier. As you can see here by the diagram, as the plane lands, it gets hooked onto a cable that then transmits the force onto two springs and a damper. The goal of this assignment is to come up with a ideal damping coefficient that minimizes the g-force experienced by the pilot and make sure that the plane stays inside of the aircraft carrier runway. Now, for this project, the runway length is 250 meters. The mass of the plane is to 20,000 kilograms, and the landing speed is 65 meters per second. To create a system that keeps the plane's displacement under 250 meters, we have to first figure out what is its equation of motion of the plane. Now, as you can see in the figure above, the displacement of the plane is dependent upon the first and second mass, M2 and M3. If you break this system down into its free body diagrams, we can see that M3 is affected by the coefficient of damping and the second spring, K2. The mass 2 is affected by the first spring and the second spring, K1 and K2. Now, from these free body diagrams, we can determine the equation of motion for each mass. First, the first mass is seen in equation 1, where we write out the equation motion for that mass, take a little pause, and then solve for x3. After we have x3, since mass 2 is dependent on x3, what we can do is write out the equation motion for m2, as we can see here, and solve out for x2. Now, having x3 and x2 allows us to plug it into the equation of motion for the plane. As you can see here, the equation of motion is a very long derivation that is just plugging in x1, x2, and x3 into the transfer function of the mass of the plane. After deriving the transfer function for the plane, we can actually put that into Simulink in order to output the displacement, velocity, and acceleration of the plane. Here is a diagram of what that Simulink model looks like, and to the right is the transfer function put it into that model. The only variable in this transfer function is the KD, which we have to manually tune in order to keep the displacement under 250 meters. After tuning and trial and error, I was able to determine the value of 30 that would keep the displacement to a minimum, or 250 meters. In order to minimize the acceleration experienced by the pilot, the entire runway had to be used. Here are the graphs outputted by Simulink. On the first one, we see the displacement over time. As we can see, it shoots very fast to 250, but it stays under that 250, which is what we were required to do. After that, the velocity, as we can see, it starts off with a very high velocity and then eventually comes down to 0, which is ideal for this situation. The acceleration, it makes sense that the acceleration jumps immediately as soon as the plane comes in contact with the damping system. The second part of the project was to design a system that also simulated landing a drone. As you can see here, the mass is a lot smaller and the initial velocity is also a lot smaller. Using the transfer function previously derived, all we had to do was change the mass and the initial velocity, put that into Simulink, and output these graphs, the displacement, velocity, and acceleration. Displacement, as we mentioned before, it has to be kept under 250 meters. After manually tuning this system as well, I was able to come up with a coefficient of damping that was 1.35. It makes sense that the damping coefficient is a lot smaller since the drone is coming in at a much slower velocity, and it has a much more smaller mass. The large difference between the damping coefficients means that this system is not ideal for different size planes, which means that the damping coefficient has to be constantly changed in order to accommodate for new, larger masses. And this explains why the Navy eventually switched to a newer system that didn't rely on constantly changing the damping coefficient in order to accommodate for the size of the aircrafts. Here is the new system for the damping system used by the Navy. As we can see in this model, the dampers are replaced with water spinners. The damping force from the water spinners changes from what the dampers was. The dampers was just the coefficient times the velocity. Now for the new damping force, we can see that it's dependent upon the viscosity of water, the area of the drums, the velocity of the aircraft, and the length between the two drums. If we take this equation and plug it into our previous damping force equation, we can see that we can cancel out the velocities, and since we have already derived a KD, a damping coefficient that needed to land the plane properly, the only thing that's left to solve for would be the length between the drums. And the length would just be equal to the viscosity of water divided by the KD, which would then give us a length of 0.33 millimeters. Using this same methodology for the drone, we can determine the length between the drums required to land it, which would be 74 millimeters.